Okay, so we're going to look at another optimization problem. This one's number 5. Before we do, just a quick reminder, if you like this video, please let me know. If there are things that you dislike about it, please let me know. So be specific in your comments because I want to make these videos best for you guys. Okay, that's my goal. So let's see what we got here. So we have a 10-foot tall fence runs parallel to a house. So here's what I'm kind of picturing here. And we have this ladder that's leaning against the house. So here's my house. And I've got this ladder kind of leaning on it. It goes all the way to the ground. And there's this fence that's kind of in between them, maybe right here. And it is 10 feet tall. Okay? Things we don't know how tall the building is. So in other words, I don't know what this is. So if you don't mind, I'm going to call it Y. And what else don't I know? I do know that the fence is 4 feet away from the wall. So that's 4 feet. I know it's kind of hard to see. Let's see if I can make that 4 a little better. That's 4 feet. Okay? What I don't know is how far from the fence is the end of the ladder. So I will say that, and I'll do this in green to differentiate it. I'll call this distance X. Okay? So let's see what we need to do. We want to minimize, find the length of the shortest ladder. So we want to minimize the ladder. So let's see what we need to do. I need something that's going to relate X and Y. So what I'm thinking is I am thinking similar triangles. So I have the small triangle, which is, I'm going to say X is to 10. And then I have the larger triangle, which is X plus 4 is to Y. Okay? And just to keep things straight here, I'm going to call that equation 1. So next, what I am going to do is I'm going to solve this for Y. And that's just going to let me put things all in terms of X. Okay? Which will be useful when I go and write my primary equations. So let's see what we get here. So I get xy equals 10x plus 40, which means y equals 10 plus 40 divided by x. And I'll call that equation 2. Okay, so that is my translation between y's and x's. So now I need a primary function. And obviously what I'm trying to minimize or maximize is the length of the ladder. Okay, so I think you guys would agree, in order to find the length of the ladder, I'm going to use Pythagoras' theorem. So if the ladder's length, we'll just call L, then I could say L squared equals that base, so x plus 4 squared, plus that height, which is y squared. Okay, and substituting what we found here into my formula, I get L squared equals x plus 4 squared plus y squared, which is 10 plus 40 over x squared. Okay, so let's do some numbering here. Let's call this equation 3 and this one equation 4. Equation 4 is obviously the big one because equation 4 is what we were trying to minimize or maximize. I'm going to highlight this in yellow. It is so important. Whoops, that's not highlighting. I'm going to highlight this in yellow because this is our important equation. This is what we're going to try minimizing or maximizing. It's those x values. Now, let's see what we can do here. First off, I don't know what the maximum value for x is, but I do know the minimum value, right? I think you guys would agree the smallest value for x could be 0. I can't figure out what the configuration would exactly look like. It doesn't even make sense, but we know we can't have negative values for x. So let's see what we're going to do here. So I want to optimize this. So I'm going to go find critical numbers of this function. I'm going to just do it as is. That's what I'm going to do. So let's see here. Just a quick note before I do any optimization. I'm going to note here that L equals the square root of that highlighted stuff. I'm not going to use this right now, and you'll see why in just a minute, but I'm just going to kind of take note of this. I'm going to use this later, okay? So that is the length of the ladder. Again, I'm not going to use it right now. I'm going to use it later. So I'm going to go back and I'm going to use, in fact, I'm going to grab it right here, and I'm going to copy it, and I'm going to paste it. So I'm going to use equation 4 to kind of do some manipulations, to do my math. So let's take the derivative. So I get 2L times the derivative of L, which is dl dx, because again, this is with respect to x. I know I'm saying dl dx, it's L prime. So if you just want to call it L prime, feel free to. In fact, maybe that's what I'll do just so it's not confusing. So dl times L prime equals the derivative of this stuff. And the derivative, I'm just going to do it as is. So applying chain rule, this is 2 times x plus 4 plus 2 times 10 plus 40 over x. Decrease that exponent by 1 times the derivative of the that inner, which is just going to be negative 40 over x squared. Okay? And let's start cleaning this up a little bit. So a couple things I noticed right off the bat is that I have a 2 that I can cancel out, which I'm going to do out of the those 3 expressions. Okay, and let's clean things up. So I get L times L prime equals x plus 4. And multiplying those things together, I get, what is that? Negative 400 x squared. Yep. Minus 1600 x cubed. Okay? And getting a common denominator, I get L times L prime equals, let's see, how about x to the 4th over x cubed plus 4x cubed over x cubed minus 400 x over x cubed minus 1600 over x cubed, which equals L times L prime, which equals x to the 4th plus 4x cubed minus 400x minus 1600 all over x cubed. Okay? So this is going to be, I'm going to have to kind of deal with this. So I want you guys to notice, and I'm going to take this equation, hope this isn't confusing. I'm going to grab this and I'm going to move it over here, and you'll see why in just a minute. I just need a little extra space. Okay? What I want you to notice is I can replace L. I can replace L now with, I'm going to replace it with this. But before I do that, I'm going to move that L over to the other side. So in other words, I get L prime equals all this stuff. Let's be lazy and just copy it. So it equals all this stuff times 1 over L. Okay? And of course, substituting in the stuff for L, I get, again, being lazy. Man, what a nice feature, right? I can be so lazy, so awesome. Times 1 over, let's grab it and be lazy again, over this stuff. Copy. Okay. Huh. Okay, I grabbed it a little bit too much. Okay, so that's what it equals. Now, you might be looking at that going, oh, that looks terrible. But it doesn't actually look terrible. And here's why it does not look terrible. I want you to notice this right here can never equal 0. Right? X plus 4 squared is a positive number. 10 plus 40 over x squared is a positive number. Positive plus a positive is a positive. So that that stuff can never be equal to 0. So the only things that I have to really worry about is that first function. So the only thing I really need to worry about is this. So my critical numbers are 0, which again, it can't be 0 because that would be, it would be behind the fence. So it's really just that numerator. So I'm going to set that numerator equal to 0, and I'm going to factor it. So let's see. I'm going to pull out an x cubed out of those first two, and I get x plus 4. I'm going to pull out a negative 400 out of those, and I get x plus 4. So I get 0 equals x cubed minus 400 times x plus 4. So my critical numbers are either x equals negative 4, which it cannot be because it can't be negative, or x cubed minus 400 equals 0. So x cubed equals 400. X equals the cube root of 400. Okay? If I go and check it, which is not a bad idea, and I go and plug this into a sign chart, what I will notice is that it is indeed a minimum. So the x value of that x value for this thing up here, this x value, we see is the cube root of 400. So I'm just going to highlight what I just did right there. I can then plug that in. Notice I can plug that in for my ladder. So I can plug it into this. Let me grab that. And I can evaluate it. So when I do, and I'm cheating, the only reason I'm cheating is I think I'm running close to my 15-minute time limit. When I plug this in, I get 19.165 feet. So that is the smallest length of my ladder.